Hello! Welcome to Statistics and Sampling. Let's begin by distinguishing two kinds of statistics, descriptive statistics and inferential statistics. We'll first define descriptive statistics as follows: numbers that characterize the central tendency and dispersion of a data set. And psychologists, other scientists as well, often look at data sets. We sometimes call these distributions of data, or data sets, and we try to distinguish one from the next by describing them with respect to these two measures. One is central tendency and one is dispersion. Many students will be very familiar with central tendency. When we're describing a data set and we're referring to its central tendency, we might use the means, the simple arithmetic average. We might use medians, that's the 50th percentile. Or we might use modes, the most frequently occurring score. For some data sets, which we also call distributions, we find that the means, medians, and modes line up. They're all right on top of each other, or they're very, very near each other. For other kinds of data sets or other distributions, the central tendency measures are very, very different from one another. And this is one of the ways that we can begin to distinguish data sets one from the next by using this descriptor, this central tendency. We also have another descriptor, and that's dispersion. Dispersion refers to how the scores are spread. There are different measures of referring to the spread of scores. The most commonly used one is probably the standard deviation, the average extent to which a score departs from the mean. So let's take an example. Let's assume that we have a collection, a data set, filled with IQ scores, and a particular IQ score is 110. The data set, though, has a central tendency that might be showing a mean of 100 rather than 110, and also a median and mode of 100. So our score then is a bit higher than the mean, median, or mode, which would be 100. There's a 10-unit difference. Is that a lot? Well, it might depend on how the scores are dispersed or spread out. Let's assume for just a moment that we have a data set that, again, has a mean of 100 as its mean IQ score, and it has a standard deviation of 20 units. In that particular data set, a score of 110 is not too different from average. It's falling within the average extent to which scores depart from the mean. 110 is not too different from 100 in that particular context. But let's take now another set of hypothetical IQ scores that have, once again, a mean, median, and mode of 100. And again, we're interested in one score that has a particular value of 110, but we'll pretend that the dispersion is different for this distribution of scores, for this data set. We'll pretend instead that the standard deviation is only 1 unit. Now, all of a sudden, a score of 110 is 10 full standard deviations away from the mean of that set. So that would be a very different kind of relationship to the mean than would be the case in the first scenario that we described. So when we're trying to describe a typical score, it helps us to understand how the data set is centrally tending and how it's spread out, how it is dispersed. These are descriptive statistics. We can contrast that with a different kind of statistic called an inferential statistic. We can define inferential statistics as a process, specifically the process of using samples to draw conclusions about populations. This idea of drawing conclusions is synonymous with drawing inferences, and this is where you can see the name inferential statistic arising. Inferences for inferential statistics. Usually, when we're engaged in inferential statistics, we have to rely on an important concept called statistical significance, and we can define this as an effect that is unlikely to occur by chance. So let's begin to unpack that. That's a difficult concept for many students. When we talk about an effect, we're talking about a trend in the data or some kind of difference, maybe between two groups of participants or maybe between two different experimental conditions. There's some kind of a difference, and we want to know whether that difference is likely to occur by chance or not. And we refer to statistical significance when we're evaluating the data in this way. Researchers often invoke what they call informally the 5% rule. Now, what is that? The 5% rule refers to outcomes that could occur by chance with a probability less than 5%. And we call those relatively infrequently occurring outcomes statistically significant. That is, they're not likely to have occurred by chance. The probability, or p-value, and that's what the p stands for over here, is less than 0.05, which is, again, 5 times out of 100. Now let's be very clear that the 5% rule is very much an arbitrary rule. It's widely adopted, but it could have been a different rule. It could have been a 1% rule, 1 chance out of 100 rather than 5 chances out of 100. Had it been 1%, this would be p less than 0.01. Some other researchers use a much more stringent criterion. They might use a 0.1% rule. That would be 1 chance out of 1,000, and that would be p is less than 0.001. So these are arbitrarily selected values by the researchers, but nevertheless, they do help us to understand the probability that something is occurring by chance. The 5% rule is the one that's most frequently adopted. If you'd like to read more about statistical significance, you can do so at this wiki. Sometimes, though, just looking at a picture helps us to understand quite a bit more. So let's take a look at this data set that has not shown very many individual numbers. Instead, we're shown the information graphically. And we're looking at some unnamed variable that seems to have a positive side on the axis and a negative side, and it seems to be centered at 0. You'll also notice that the mean, median, and mode tend toward the value of 0, and as you move away from 0 in either direction, you tend to get a decrease in the probability of those scores. What's very interesting is that 95% of the scores are shaded here in blue. At this end, at this tail as we call it, we have the highest 2.5% of the scores. And down here in the lower tail, we have the lowest 2.5% of the scores. If we take 2.5 from down here and 2.5 from over here, and add those together, 2.5 plus 2.5 will get us to the 5% that we were referring to back over here when we were describing the p-value of 0.05. So you can see that this is referring to these relatively extreme scores as being statistically significantly different from the center of the distribution. These don't occur very often. They might occur by chance, something like 5 times out of 100. Okay. We do have ways of describing the errors that we might make when we're trying to draw these conclusions about populations when we're looking at just samples. We always could be making an error, and psychologists and other scientists have ways of describing the errors that they might be making. One type of error is a type 1 error. This is a false positive. And we track this with something called an alpha level, the probability of a type 1 error, or the probability of a false positive. Usually we set our alpha level at 0.05, just like we saw in the preceding slides. That's the most commonly used alpha level. Let's give an example of a false positive. Let's pretend that you're a psychologist and you're interested in alleviating depression in college students. So you might take a sample of depressed college students and expose half of them to your treatment. Maybe it's a cognitive behavioral treatment, and you think that you can alleviate depression by using your treatment. Another control group might receive no treatment whatsoever. And after a few weeks, you'll notice that you make a measurement, and one group has a higher mood score than the other one does. And it turns out that that score occurs less than 5 times out of 100 just by chance. Well, then we would say we have a statistically significant effect, but we might be making an error because you could have gotten that kind of a difference 5 times out of 100 just by chance alone. We can contrast this type 1 error with a type 2 error, false negative. Staying with the same kind of example, it could be that when you look at your group that has received your treatment and the control group which has not received your treatment, there are really no differences for this particular sample. However, it might be the case that if you ran this test many, many times, you would find that your treatment really does work. You just happen to come up negative this time, so you missed it. Okay? So we would call this a miss or a false negative. That would be the other kind of error that you can make when you're engaged in inferential statistics, trying to draw inferences or conclusions about populations based on samples. And here we have the complementary kind of level. This is the beta level versus the alpha level. As one of these increases, the other decreases, as you might imagine. Okay, let's move on and learn a little bit more about populations and what we mean by that. A population is every member in a group of interest. One possibility would be that you and I as psychologists are interested in all college students. But for practical reasons, we're reduced to taking just a sample, a subset of that population. And that might be, as one example, the psychology students at a particular university. Maybe it's Denison University. So this would be a sample, and we might investigate this sample, but we're really interested in drawing some inferences or conclusions about this population. Here's a simple diagram that shows the idea of sampling. Here's our population, and we can now put maybe a number into a hat, metaphorically speaking. We have 12 members of our population, and 12 numbers go into our hat, and we pick out a sample that's a little bit more manageable, and we randomly pick, say, 2, 5, 8, and 10, and we use that as our sample to help us more fully understand the population. This sample is more manageable, and here we're using simple random sampling. That's one kind of sampling technique. There are different varieties of sampling techniques. The one that we just looked at, so-called random sampling, is a technique for selecting a subset of a population. And each member of the population has an equal chance of being selected, as was the case in our hypothetical numbers out of a hat paradigm. Random sampling is preferred because random sampling generally grants the highest levels of representativeness in the sampling process. And that's what we'd like to see. We'd like to have a sample that is, in many ways, very representative of the population. However, there's always a catch, and that is that for practical reasons, we often have to resort instead to something called convenience sampling. Now, this is similar to random sampling in that it is a technique for selecting a subset of a population, so it is a sampling technique. But here, members are selected based on practical matters, like the availability of participants for a particular study. Ideally, we'd be engaging in random sampling. More frequently, we have to make do with convenience sampling just for practical reasons. Okay, thanks for listening.